Welcome back to The Explainer. I am absolutely thrilled you're here because today we're going to bridge a massive gap between the things you can actually touch and the incredibly complex, invisible world that builds them. Have you ever stopped to think about how huge the disconnect is between what we see in our everyday lives and what's fundamentally happening at the microscopic level? We live in a macro world, but it's entirely dictated by microatomic mechanisms. If you look at the split screen layout on your screen right now, you'll see exactly what I mean. We're going to zoom all the way in and decode the hidden rules of chemical bonding that govern the tangible, physical properties all around us. Let's kick things off with a classic, everyday mystery. Take regular table salt disappearing into a glass of water, for example. I mean, it seems like magic, right? A solid crystal structure just vanishes into a clear liquid. But check out the magnified insert bubble on screen. What's actually happening at that boundary layer between the water and the salt? The answer entirely depends on the invisible chemical bonds holding those salt atoms together and exactly how they react when introduced to the bonds within the water. Okay, mystery number 2. Why is a diamond literally one of the hardest natural substances on Earth? It's made of the exact same carbon atoms as the completely brittle graphite in your pencil. How can the exact same building blocks create a material that smudges on paper and another that can literally drill through solid rock? I'll give you a hint. The structural secret lies entirely in how those microscopic atoms are sharing their resources. And for our final hook question, notice how energy easily flows through this copper wire. You can see the directional vectors showing the movement right there. Why do metals conduct electricity and heat so incredibly well, while the plastic coating around that wire completely stops the flow? Understanding these exact material properties isn't just a fun trivia exercise, it's absolutely crucial for real-world engineering and, importantly, for scoring high marks on your chemistry exams. Because if you can explain the microcause, you can always predict the macro effect. So, here's our roadmap for today. We're going to cover the chemistry of everyday materials, break down ionic, covalent, and metallic bonds, correct some common exam mistakes, and wrap it all up with a final recap and some exam tips. We've got a clear path ahead, so let's jump right in. Section 1. The chemistry of everyday materials. Section 2. Ionic bonds, electron transfer. All right, let's dive into this, starting with ionic bonds. The absolute keyword you need to lock into your memory here is transfer. We're talking about the complete handover of electrons from one atom to another. Follow along with the flowchart here. In step 1, think of it like a basketball player just completely passing the ball to another without ever getting it back. Notice how the sodium atom entirely loses an electron. Now, the current step highlights step 2. The chlorine atom gains that exact electron. Finally, in step 3, this complete transfer creates oppositely charged ions. The sodium is now positive, the chlorine is negative, and notice those thick arrow vectors showing the pole. Just like magnets, they powerfully attract to form a stable compound. Now, you might be wondering, why does this happen? Why is sodium the passer and chlorine the receiver? Well, it comes down to ionization energy and electronegativity. Metals, like sodium, have a super low ionization energy, meaning it takes very little energy for them to just drop that outer electron. On the flip side, and notice the visual scale indicators here, nonmetals, like chlorine, have incredibly high electronegativity. They're super eager to pull electrons in. When you put a metal that wants to give up an electron next to a nonmetal that desperately wants one, this precise transfer mechanism is pretty much guaranteed. Section 3. Covalent bonds, sharing pairs. Let's move along and see how this builds when we introduce atoms that actually don't want to completely give up their electrons. If ionic bonding is passing a basketball, covalent bonding is way more like a successful group project where everyone chips in equally. By overlapping their outer valence shells, and you can see that structural overlap labeled clearly right in the middle there, they share electron pairs. Both atoms get to basically count those shared electrons as their own. This mutual sharing allows all participating atoms to fill their valence shells and achieve structural stability. Let's walk through the steps with a real-world example, forming a water molecule. Highlighting step 1 here, oxygen needs 2 more electrons to be stable. Moving to step 2, the hydrogen atoms each need 1. Now watch what happens in step 3. They don't transfer, they lock together. Each hydrogen atom shares 1 electron pair with the central oxygen atom. This clear overlap securely forms incredibly strong covalent bonds, ensuring that vital stability for all 3 atoms involved. Section 4. Metallic bonds, delocalized electron C. Now, let's shift focus to our third and final bond type. And honestly, the atomic structure here is absolutely fascinating. This isn't sharing, and it's definitely not a direct transfer. Picture a massive crowd at a concert. The positive metal ions are fixed in place. They're the stationary pillars. But the electrons, they're the crowd. Notice the movement vectors on screen. These are free, delocalized electrons constantly swirling around those stationary ions. The electrons don't belong to any single atom anymore. They're a shared, highly mobile sea that freely washes over the entire structure. So the crucial point is exactly how this structure defines a metal's physical properties. Remember our hook question about the copper wire? Because this sea of delocalized electrons is already incredibly mobile, when you introduce an electric current or heat, those free electrons act like a high-speed transit system. You can literally see the flow vectors carrying that energy right from one end of the metal to the other. That precise mobility is exactly why metals conduct electricity so brilliantly. Section 5. Common exam mistakes corrected. Now that we've mapped out the micromechanics of all three bond types, let's transition into some exam prep. A very common myth is that ionic compounds, like a grain of salt, exist as isolated individual molecules just floating around. Actually, scratch that, it's totally false. Look at the side-by-side comparison here. As you can see on the right, they form giant continuous ionic lattices. It's millions of positive and negative ions stacked endlessly in a repeating 3D grid. It is not one sodium paired with one chlorine. It's a massive, structured neighborhood of attraction. And this brilliantly illustrates the solution to our diamond mystery from earlier. The myth assumes all covalent compounds are weak gases or liquids, like water or oxygen. But in reality, some materials form giant, solid covalent networks. Look at the structure on the right. In a diamond, every single carbon atom shares strong covalent bonds with 4 other carbon atoms in a super rigid 3D web. And that is exactly what makes a diamond remarkably hard. Section 6. Final recap and exam tips. All right, let's synthesize this whole thing. Ionic bonds feature the complete transfer of electrons, which results in the property of giant crystalline lattices. Covalent bonds, the mechanism is sharing pairs, which allows atoms to achieve filled valence shells and distinct molecular shapes. And metallic bonds, characterized by a delocalized sea of free-moving electrons, perfectly explaining why metals are incredible conductors of electricity. Clarifying exactly how the microbehavior dictates the macro property is absolutely key. To secure those top marks, here are your actionable exam tips. First, always draw incredibly clear dot and cross diagrams. If you're showing an ionic transfer, explicitly draw the directional vector of the electron leaving one shell and arriving in another. That visual clarity proves your understanding. Second, don't just memorize definitions. Practice explaining why. If a question asks why a substance conducts electricity, trace it back step by step to the specific mobility of its electrons based on its bond type. I want to leave you with this final thought. Take a second to literally look at the objects around you right now in your room. The glass in your window, the metal in your phone, the salt on your food. None of it is magic. It is all math, physics, and chemistry operating beautifully on a microscopic scale. So, which of these invisible chemical bonds are holding your physical world together right now? Keep asking questions, keep looking deeper, and I'll see you in the next explainer.